those were some great talks, and they've kind of, I think, set the stage for some of what I'm going to talk about. And actually, when Ken contacted me about this, he was looking for places where technology had or some process had kind of plateaued, and there was a lot of work done, and there were subsequent breakthroughs. And so my first thought was that I would talk a bit about Sudbury, which we've talked about a lot before, where it was considered in 1970 to be a mature camp with no further possibility of discovery, had a reasonable price. They were deep drilling to 2.5 and 3 kilometers if they hadn't found anything for 20 years. And then all of a sudden we got really good, exactly the right borehole EM system, combined with some really good geology done up front. And I think this is just tying into what John said. It's the combination of the fancy technology with really good geology that made the difference. And all of a sudden there was a string of discoveries in Sudbury that's still going on, and there was a number at Inco and Falconbridge, and then FNX has continued the trend with the new Victoria deposit, which is a new high-grade deposit, 10 million tons found and announced, I think, in 2012. So, but anyway, as I was putting that together, I realized it was actually a bit bigger story, and that's the problem of exploring for high conductance targets with EM methods in general, as successes and challenge. So I've just generalized it a little bit, so I'll just start through it, and you'll see how it goes. Yeah, first of all, I'm going to put the acknowledgements up front, because I usually forget it. A lot of people have contributed to my thinking over this, and I've learned from all these people, particularly Gordon West, who was my professor of geophysics at U of T, and I was actually key in the fundamental work in this particular area. Yves Lamontagne, one of his best students, and all these people from Duncan McNeil from Geonics, Ben Polzer at Valley, the Inco Valley exploration team, particularly Barry Krause and Eberhard Baer, who have retired from Inco and Valley a long time ago, but they were the ones who correctly picked the right system, the right time, got some fantastic results, and hired me basically to run it. So I was just in a very fortunate position. Gordon Morrison and Andy Byte, who were the geologists, who picked the right ground to do the geophysical surveys in. And I think that's the key here, and if we have a magic bullet, it's putting all these methods together, geochem, geophysics, and geology. It's not one bullet, it's a combination. The Boise Bay exploration team, Steve Balch in particular, Falconbridge, I've talked a lot to Tony Watts about this, and the people at Falconbridge, there's a lot of good cooperation. Bill Raidhurst from Crone, the Australians, I call them collectively Bella Mann, who introduced us to moving loop E-field EM in Australia, Andrew Duncan, who built a lot of the equipment that we use. The Anglo-American exploration team with their work on low temperature squids, and the IPTH who built those squids, and Dennis, who's here. And these are all people whose work I've looked at and whose slides I've borrowed and pictures. So, and in particular, just the ones in red actually reviewed the paper and gave me some very constructive results, not all of which I've been able to incorporate, unfortunately, just because we have time limits. So, the problem. This was I'm going to be talking about EM systems in general, in particular time domain EM systems. And after sort of a good start in the 50s, 60s, and 70s with frequency domain EM systems, the whole industry just changed over from frequency domain EMs, which transmit a single frequency, to pulse systems, which transmit a big dirty pulse all at once. And that was a revolution and led to a whole bunch of discoveries of VMS deposits and other ones, and it was highly successful. But then it kind of plateaued a bit. And one of the reasons for that is the traditional 25 to 30 hertz pulse type time domain EM systems that measure when the transmitter is turned off do not detect or resolve very good quality large conductors well. These systems have found lots of good conductors, in particular lots of EMS deposits and lower grade copper nickel deposits and ore bodies, but are likely not to detect large excellent conductors or they are likely to misclassify them as not such good targets, particularly at depth. Now, and this is actually still happening now, because if you look at that, most of our airborne systems that we rely on for our reconnaissance and wide area mapping at a low cost are still 25 hertz pulse type time domain EM systems. So I'm going to talk about that bit, and at the end maybe what we can do about this. And there's been a lot of key work done by people to kind of push this problem ahead, and there's maybe a few other things we have to do. So there's a lot of different people here, and this is going to be a bit of sort of some gory details of geophysics. I don't think there's any equations, but I'm just going to make some definitions up front. And we hear these terms all these times, and one of the things I wanted to do in this paper was just get them down on paper for my own purposes as well as other people. So B field, that's the magnetic field in electromagnetic systems. So it's the M in electromagnetic. It's created by the electrical current flowing in a transmitting loop. dB/dt, that's the rate of change of the magnetic field with time. You cannot have an electromagnetic measurement or electromagnetic induction without a changing magnetic field. A DC magnetic field like the Earth's main field is not good enough. Frequency domain EM system, that's an EM system that transmits a single frequency at once. And those are, it's like a single note transmitted at once, high C, and then you transmit another note, and then you transmit another note. Those were the original EM systems. Time domain EM system, it's an EM system that transmits and receives EM pulses that contain many frequencies at once. It's like a chord in music where you play a chord. An off-time EM system is a time domain EM system that measures when the transmitter current is off. An on-time EM is a time domain EM system that measures when the transmitter current is turned on. So, this is a frequency domain EM system, just like the sinusoid current 60 hertz flowing in the wall. This is a time domain EM system right here. Yeah, so at the top is just a frequency domain transmitted waveform. They all look the same, just different frequencies. And most of you are familiar with some of those systems, the old standby max-min, helicopter EM systems, and the old, interesting enough, the old Inco airborne EM system, which is one of the first airborne EM systems. A time domain system, on the other hand, transmits many frequencies at once by transmitting more of a chord instead of a single node. And at the top, you can have many different kinds of waveforms. There's almost as many different waveforms as there are companies or geophysicists. Everybody has their own continuous triangular, continuous square wave, a pulse system where you turn it on and then off, negative, on, off, on, off. And I've just named all the systems here. This is Geotem, Spectrum, Tempest, Chrome, Geotic, Cybertem, etc. And most of the airborne systems down here. This is an EM schematic, and again, I'm just sort of building up the terminology here. I think EM is the least well understood of all geophysical methods. It's probably the least intuitive, but just to go over it, this is a schematic of any particular, no particular EM system. We have a transmitting loop where we pass current through a wire, and we change that current with time. So we have a primary current that generates a primary B magnetic field that alternates with time. That generates a low frequency radio EM field, or otherwise known as a radio frequency field, but it's just low frequency radio energy, and it propagates through the Earth. It interacts with an ore body, and the changing magnetic field causes a current to flow in the ore body, and that that current flow in the ore body generates another magnetic field that's changing with time that sends secondary radio frequency, low radio frequency energy back up, and we measure it somehow with some kind of receiver here which measures the B field or the rate of change of B field. Now, the problem. This is a schematic of a single time domain EM pulse measured with a dB/dt coil, or typical receiver coil for various targets. And this is just a typical traditional airborne ground borehole pulse system. So you can see that here's the response of a weak conductor. So in early time, you get a very strong response, and this might be a narrow vein, a weak conductor, poorly conductive VMS target. A good conductor is a good, thick, sulfidic, pyritic VMS deposit. And you can see that it's sort of in the mid-range of the system, but the problem is, an excellent conductor that has very slow decay coming back from the ground has almost zero response to the mainstay of our exploration systems. So this is a very busy figure, and I'm not going to be able to go through all the details here, but most of them are in the text there. So this is the response diagram for any particular off-time dB/dt EM system, including input Geotem, most current Heli systems, and all the old ground pulse systems. So the main thing to notice is that, I won't point at that one, is that there's an aperture here. So obviously there's no good response to a very weak conductor. Down here below 1 Siemens per meter, or 1 Siemens, which is the way we measure conductance, 1 Siemens is very low conductance, 10,000 is very high. So you don't see really poor conductors. You don't see weak alteration, you don't see changes in water, resistivity, you don't see zinc deposits. If you want to look at these things, you switch to really high frequency domain systems that have much higher frequencies. So, and now, but what most people don't realize, and I didn't before I started at Sudbury, was that this thing dies off at very high conductance. So we're measuring in 10 orders of magnitude, 10 steps up in quality of conductance. So this would be considered a very good conductor, 1,000 Siemens target. And so eventually, at what we call excellent conductors, the signal from this basic system actually goes to 0, and you don't see the best targets. Now, why did we do that? We used to have good airborne EM systems, frequency domain, they'd find anything, but the old frequency domain EM systems, like the early ones, they had very weak signals, small transmitters, and very little penetration, and they also had a big problem controlling their geometry because the transmitter was turned on all the time. We'll talk about that a bit later, but the key is, right in here in the middle, in the sweet spot of the airborne time domain EM systems, which was originally input, and Geotem and Megatem and all the helicopter TM systems now, is the sweet spot for VMS deposits. And that's what they found. If you think back, that's what we found tons of with this. And they worked very well. So they were duplicated on the ground, and they were duplicated in the borehole systems. And I just define aperture. That's the window that the system can resolve systems at. And just a couple of definitions. I'm going to be talking about conductance. That equals conductivity times thickness, and that's measured in Siemens. So you'll see a lot of 5,000 Siemens and 500 Siemens. Okay. Now there's good news and bad news in this. The bad news is that most very large high conductance targets, especially at depth, a long way from your transmitter, have been missed or misclassified in most standard TEM surveys, including all of our airborne surveys. The good news is, and the problem is particularly bad for airborne, because we can't operate at low frequency. The good news is, there's a lot of large high conductance targets at depth to be especially deep. And this is the problem in a bit more detail. So most modern deep penetrating EM systems use high power time domain EM systems. EM target quality for a tabular conductor is proportional to conductivity, thickness, and lateral dimensions. And its target quality is actually not best represented by the conductivity or thickness. That's not what really our systems respond to. It's the rate of decay of the secondary signal from the ground. And that's measured by a parameter called tau, which is proportional to the conductance of the target, which is conductivity times thickness, which is a good conductive thick ore body, times its size. So that's really what you want. You want it big, you want it thick, you want it very conductive, and you want it big. So I'm going to be talking a lot about tau, and that's really the fundamental parameter you want out of your system. It's independent of system. It's dependent only on the target. Okay. So I'm not going to read all these out loud. You can look at them and look at them in the book, but if tau, the rate of decay of the signal coming back from the ore body, is considerably longer than the time you've got for reading with your system, and with an airborne system you're moving across the ground pretty fast and that you don't have a lot of time to spend there, if it's considerably longer than your time window, the secondary currents from the target in the ground don't decay much during the measurement time, and the measured rate of change of the current in the target in the ground goes to 0. So, translation. For large, very high conductance targets, the measured dB/dt signal measured in the Offtime goes to 0. And it's particularly acute with very large tau targets because of the slow decay of the response. And it's not just related to high conductance. So it's a problem for very good quality conductors and very big conductors, which are our principal target of interest. Why do we care? The ovoid was the one that really crystallized our thinking on this. We see a lot of these at Sudbury. These high conductance targets do exist. You all know the ovoid at Sudbury. It's a great big 32 million ton, totally massive pyrrhotite, pentlandite, and a bit of chalcopyrite deposit. The conductivity of pure pyrrhotite, absolutely pure on a single crystal, is about 100,000 Siemens per meter. Approximating the deposit by a 100-meter sphere at 100,000 Siemens conductivity, we get an approximate time constant of 120 seconds. Now I'll show you why that's important. So there's little or no decay in conventional systems, and you don't see it that much. You don't see it that well. And these are just the examples from Boise Bay. This is by a paper by Steve Balch, published in 1995. And this was the real deal data over the deposit. And as we were looking at this, we were learning. So on the top there, that's a response of a 30 hertz UTEM system, which is the ideal system for measuring high conductance targets. And you can see right in the middle there, in the channel 1 non-decaying on-time response, there's a nice big negative that exactly shows you where the massive current in the ore body is. With an old-time helicopter frequency domain system, you can see the ovoid perfectly well as well. But this is a airborne pulse type system, and amazingly enough, it doesn't see the main ore body. There's an anomaly here, but the response is of little currents flowing on the side, right in these corners here. And because the system doesn't have enough aperture to pick up that high conductance, you don't see the response. The response, this is the Geotem response of a horizontal conductor, and it's in the Z, and it's just not there. Another example, we did a lot of borehole work. This is just a synthetic model study where we just get rid of all noise factors. We've got total control on the system. I'm just showing an example of a 500 Siemens target and a 5,000 Siemens target. And again, this is for magnetic copper nickel sulfides, where 500 Siemens is actually not a very good target, and 5,000 Siemens is ore. So I did a model study. I put in a somewhat larger 500 Siemens target, and the target you're looking for, the mass of ore, is a little smaller pod of 5,000 Siemens material over here. And on the right, highlighted in blue, is the response from the 500 Siemens target. On the left is the response from the 5,000 Siemens target, what you're looking for. And you'll notice that you've got a really big response over here, because you're right in the middle of that sweet spot in the time domain EM system. And this one's just right on the tail, and if you really squint right there, you can barely see it. Now the problem is, if you do it in plan view, and we use the XYZ component to tell us which direction to go, I put them on opposite sides of the hole. If you only use the Offtime DBDT data, you're always going to drill this. You'll explain your big anomaly that hits you over the head perfectly, and you'll never even know that this one's here. So there's some solutions. You can work with system geometry, transmitted waveform, measured parameter, receiver type, and data processing. So one, you can do it the old way. You can measure while the transmitter is on using traditional frequency domain EM systems. You can measure or calculate the B field at the receiver. You can measure or calculate the B field at the TEM receiver. You can use modern high-power TEM systems that include on-time measurements. Or you can go to very low frequencies with very sensitive B field receivers. All of these solutions work and have found high conductance large tau ore bodies. So doing it the old way with frequency domain EM systems. So if you measure while the transmitter is turned on, using traditional frequency domain systems like the MaxMin, the old Inco airborne EM system, the GDK airborne system, Digium, Boliden, borehole, etc., you get a really good response. The problem is they're very low power and you have less penetration, especially in areas of conductor overburden, and for example, in Australia, they just don't work. However, you can find good ore bodies with systems like this. This is the original data from the Thompson discovery with the Inco airborne EM frequency domain EM system. Depth penetration was limited, but the deposit was at about 100 feet, under 70 feet of glacial conductive material, moderately conductive material. So there's the response right there. And it was fairly diagnostic, and this is just going back to what was talked about in these previous presentations. This is one of the first airborne EM systems ever put up in the air. I think there was one other system in the lab, but this, I understand, was the first one flying commercially. In the first year, they found Thompson, and they flew for 20 or 30 years afterwards, flying most of the greenstone belts in Canada. They never found another major deposit. They found lots of little ones, but they even overflew Kit Creek, but they didn't find the other deposit because they'd done 20 years or more of geology before to get this system in the right place. So it was the right technology, new technology, in the right place that immediately led to discovery. And then they got totally blinded by this miraculous silver bullet geophysical technology and flew it like crazy. They flew 1.6 million kilometers, and never found another major ore body. They found lupin, they found Casperardi, they found tons of little things, but they never found another big one. And it was because the geophysics took over the group, and they just flew and flew and flew. It was the combination of geology and geophysics that made things work, and it worked immediately. It worked in this was in the first year of the system flying. They also found heat steel that year too. Okay, lots of words here. I'm not going to read them all. So you can measure, to help with this problem, instead of measuring the rate of change of the magnetic field at the receiver coil, you can use various tricks or equipment to measure the magnetic field at the receiver coil, which gives you about another order of magnitude in that aperture I was talking about. So here's just some examples. This is our transmitter coming along here, turn on, and all of a sudden we turn it off. So we've got a nice electromotive force going into the ground. This is the dB/dt decay measured with a coil, a typical coil from an airborne system, a ground system, or a borehole system. Excellent conductor, almost zero response. Weak conductor, terrific response. Now, if you measure the B field at the receiver instead of the dB/dt, this is the easy one to do. This one's a bit harder. A weak conductor response looks like that. A good conductor looks like that. And an excellent response has a really strong signal. So this actually should solve all our problems. I'm just going to skip this. Okay, I'll just go back to this. However, it doesn't quite, because right here, I've got a single pulse. This is a single pulse, and I've got an excellent response. And if I've got a very, very good conductor, this just keeps on going up like this. Now the problem is, this is a pulse system. I've got 10,000 of these pulses I'm measuring at once. So back here, 10 milliseconds before, I've got a negative pulse that generated an excellent response going the other way. And if the decay is really long compared to the repetition system of the system, this pulse exactly cancels this pulse. And they always keep canceling each other. So you have this terrific signal that just gets canceled by the opposite pulses. Now, why do they switch pulses all the time? It has to be done for the electronicity. You just can't keep transmitting the same polarity all the time. So B field helps, but it only buys you about another decade. So this is an example of in 1988, and it was first implemented. The first survey I saw was for an airborne EM survey at Voisey Bay, where we very much wanted to see longer decay times. This was the aperture I showed you before for the dB/dt receiver, and here's the aperture for the calculated B field. So instead of measuring the B field, they integrated the received signal to get the B field. So it buys you about another decade at the top end. You can see the difference up here. So instead of stopping at 1,000 Siemens, maybe you're able to get up to maybe theoretically around 10,000 Siemens, but this is in an ideal case. In fact, this is the system noise from within a perfect system. In fact, we always have geological noise in here that can just limit that bottom end there. So now the other way to solve the problem is measure the B field. That's being done routinely now, and this is the norm in Australia. They have very nice flux skate B field magnetometers, 3-component, that are used on the surface and borehole, and they work really well. The other solution is SQUIDS, superconducting quantum interference device, and they are extremely sensitive AC magnetometers, and they're used to measure extremely subtle magnetic fields. There are high temperature SQUIDS developed by the CSIRO and operated by Crone, and low temperature SQUIDS. And we'd all like to be using these. However, there are some logistical limitations. You need liquid nitrogen for the high temperature SQUID and liquid helium for the low temperature SQUID. Now, one of the other limitations, and we'll be talking about this a bit more, is that my understanding, and Dennis may correct me on this, but I don't think they're that good for measuring in the on time due to the large dynamic range required from going to that big pulse when you're on to the very, very weak pulse when you're turned off. That's just a picture of the LANTEM SQUID system developed by CSIRO and operated by Crone Geophysics. This is the IPHT high temperature SQUID system. And I'm just going to skip that, it's taking too long. Now, one of the things I wanted to do during this talk was not just talk about new technology, but I want to show how all these systems are finding new deposits. And it's a bit of a difficult time in the industry now, but in spite of that, people are pushing the limits, the bounds on all these systems, trying to make them a little bit better, and we're finding a number of really nice new deposits. In particular, some of you may have heard of the Sakatti discovery in Finland. It was a geochem. They were brought in the area by good geology, mag target, and base of till chemistry, I understand. They drilled for a while on that, but my understanding is that eventually they did a survey using the Anglo-American low temperature SQUID system, which is proprietary to Anglo, and they identified very much better conductivity and depth, and they drilled into that, and that's got them into the real high grade. The Nova discovery, copper nickel sulfide in Western Australia by Sirius, was discovered with the moving loop ground TEM system using a fluxgate B-field receiver. That's just a little bit of background on the Sakatti, more on Sirius Nova, pictures of that. Oh, I just want to go back. And this is from the Nova discovery, and these are from the Sirius Resources Australian Stock Exchange releases that they're estimating conductances of a minimum of 5,000 Siemens. So these things really exist. That's just an example of some data from the field. Now you can use, the other solution is to use modern high-power TEM systems that include on-time measurements. In other words, we're going to stay in the time domain. We like the high power and ease of use of the time domain pulse system, but we're going to try and measure in the on-time as well. And the reason it wasn't done before, and it's not done routinely, is that it's very difficult. It's much more difficult measurement because you always have the transmitted field present at the receiver at the same time as the secondary field coming back from the ground. So you've always got the very powerful primary field and the secondary field at the same time. So you have to find some way of taking out the primary field, and it's fraught with technical complications, and it adds a lot of noise to the system. So the Lamontagne systems do that by nature from the way they were designed. The Krone TEM system and the Geonics ProTem system have both adapted to produce, with some clever step processing, to produce both on-time and off-time data at the same time. And if you're doing a survey by Krone in particular, they deliver that if you ask for it. And a lot of times people don't ask for it. And in particular, Bill Ravenhurst just said, I should add, any modern system that records the full waveform or time series, you can pull anything you want out, on time or off time. So this is all available out of existing data. You just have to know what to ask for. So here's an example again. This is from Yves Lamontagne, who was actually working on this while I was preparing this paper, and he gave this to me after I talked to him. He's got some new modeling code that actually can exactly represent these extreme conductors. We never really had code that could do this well before, so there's always a lot of discussion as to what these responses really look like. So here's the model UTEM response over the very well-known ovoid. The transmitter produces a large, very, very slowly decaying current that flows horizontally in the ovoid, and that generates this great big 50% anomaly over the deposit, and that's absolutely characteristic of this big system. So you can drop that down 400, 500, 600 meters and still see that. Exactly the same system modeled with a B-field receiver in the off time. So you're measuring the B-field, but you're not measuring the on time. Shows these small currents flowing on the side of the ovoid, but it doesn't pick up the main system here. And this is even going to low frequencies. So it's seeing, and there's been a lot of disagreement over this, these systems actually see nice anomalies on the flanks of this thing. And they say, well, we found it. Well, if you actually do the analysis on these are just a few millisecond decay, and they give you a 50 to 100 Siemens target. You don't know that you've got a 100,000 Siemens massive ore body there. It's sitting here in the middle, completely blind, because it hasn't created any signal for your receiver to pick up. It's these little currents flowing on the side, which have nice, fast little decays that give you your big response. So you don't actually miss them entirely if they're close, but you can totally misclassify them. And so you're looking at a field of 50 to 500 Siemens targets. And look at any TEM system, it's all 50, it's all 10 to 200 Siemens from every airborne system in the world. There's no 10,000 Siemens target there, and there's no 0.1 Siemens target, because you're right in that aperture, so you're blind on both ends. Yeah, so why do on-time systems work so well as compared, and why don't they have the problem that the off-time systems have that I showed you before? Well, an on-time system can either be one of these pure sinusoidal systems, or it can be that square wave I was talking before. Just sometimes you have to be measuring when the transmitter is turned on. So here's an off-time pulse measurement. Weak conductor, good conductor, excellent conductor. Here's an on-time, or some people call it step measurement. Here's the very weak conductor, here's a good conductor, and here's a excellent conductor. And so you sit up at about 100% response for a perfect conductor. Now why do they do that? Whereas all the off-time systems eventually, if you get a good enough conductor, they disappear. Well, the physics is a little bit different. When the transmitter current is changing, in other words, you're powered up and you're driving some signal into the ground, the primary EM field is driving a voltage into the conductor in the ground, and that's creating a current that's flowing at that time. The secondary current is right there all the time, opposing the primary current. And it actually acts by Lenz's law to oppose the change in the primary field. So if you're driving that system while the transmitter is on, it's driving back. So the secondary field is always present and it's always 100%. So if you measure when the transmitter is on, there's no decay. You're driving a system that's always responding back to you. So the physics, oddly enough, is quite different between on-time and off-time measurements. Okay, let me go. But there are problems with it. The on-time systems are highly dependent on accurate control of the system geometry, because you've got the primary field there all the time that you have to subtract out. Anybody that's operated a max min knows that if the transmitter is a little bit tilted or in the wrong place, your data is going to be garbage. You get a response from magnetic rocks, which corrupts the data. And as Andrew Duncan from Australia reminded me that it's almost impossible to do on-time measurements with moving loop EM, which is their major method in Australia. I'm going to have to go pretty fast because I have 3 minutes left, but just to mention that there was using the right type of system, on-time B field generated a huge wave of high-grade discoveries in Sudbury from '89 to the present. 70 million tons of high-grade ore, estimated value in the ground $27 billion, not 43101 compliant. Picture of the ore body. Now, just one thing to remember, it's not just copper, nickel, magmatic sulfides that are very conductive. If the ore body is quite conductive, like the new discovery at Lalore, and it's big, the time constant goes up, and the detectability for regular systems goes down. So you have to go to late times, B field, and on time if you can. Just a bunch of examples there. And I'm just going to zip to the end. Okay, we're getting to conclusions. I've got 2 minutes left. So what do you want? Some combination of late time, off time, late time measurements, B field, or on time EM. It's a bit harder. Some places, and sometimes it's an order of magnitude harder, but it's worth it because of the discoveries. Sudbury, the Reed Book at Boise Bay, Raglan, Sierrastova, Sakati, and Lalore, they all show that these things are around, and if you do the right survey, you'll find them. A combination of all three, all systems will help you see these large, slow decaying systems, and a combination of all three is best at very low frequencies, because if you can see a bit of a decaying response at the low frequency, it can avoid some of the problems with geometrical or DC magnetic field errors. And these are available in most modern systems. We've got some problems to resolve. We can't do it in the air yet. We need low frequency airborne EM. It would be a critical thing to get. ZTEM is kind of an interesting solution, and we need to break the 30 hertz barrier. And the main problem is the receiver bird moving the Earth's magnetic field. General problems, it's hard going below 1 frequency. We start seeing strong IP effects. We need much better, cheaper systems. And there's this nasty new thing called superparamagnetic responses that have been corrupting late time EM responses lately, and have only recently been discovered. Finally, closing comments. The problem is worse for large or deep, distant or deep conductor systems that are far from your borehole or deep in the ground. If If you're close to a large excellent conductor, you see smaller scale currents, but they don't reflect the full size or quality of the system, so you don't rank it properly. The largest current systems have the slowest decay. These are the biggest ore bodies at depths. You can use airborne EM for very high conductance targets because you'll see a bit of a response, but you have to go on the ground to see the full decay. Low frequency EM systems are getting in the range of IP, and we're starting to see IP responses. Tomorrow, EM systems are like golf clubs, and make sure you use the right one. And I've got 19 seconds left.
Quick question. The systems, the helicopter systems with the big loops underneath and the receiver in the center of the loop, does that work pretty well in terms of controlling the geometry?
None of those systems measure true on time because you have to control the geometry to within millimeters, and they do not stay for that. The only one that did was Aerotech, Steve Bulge put this bill to really control that geometry. But as soon as you get into bigger systems, they get a bit flawed, just a few centimeters, and destroys your on-time information. There's no on-time pulse airborne EM system.
Good answer.
It's a fundamental problem.
Yeah, good answer. I didn't realize that. Yeah.
And sorry, go ahead there.
Yeah, I should clarify that dynamic range of the low temperature squids. The earlier models were limited for sure, but the latest ones in the last few years, they have two settings. There's a high 630 and a low 630. You get 6 out of 2 channels, so you kind of solve that problem.
Okay, good. I didn't know that actually. I should have asked you beforehand. I should have put a question mark beside that. And I just put up just for fun and to remind people that it's magnetic fields we're measuring in EM, not electromagnetic fields. The ultimate conductor and the low frequency TM system is the Earth's molten core, which is like a 10 million Siemens conductor, and the Earth's magnetic field, which flips every million years, and it's a perfect TM system, and with good penetration. But it just reminds you that it's magnetic field that we're measuring, and radio fields propagated through the Earth. Thanks a lot.
Thanks.